Yeah, it's Math 111. Today we're going to start talking about Chapter 7, which is entitled Radicals. And in particular, today we're going to talk about Section 7.1, Radical Expressions. Radical. I wonder where this word came from. I prefer the expression root for reasons which we'll see later on today. Root is the simpler and more intuitive word to use rather than radical. Our book uses the word radical when describing radical type equations, so I suppose we're honor bound to keep with the book and terminology here. Well, I'm guessing you know about radicals or roots. What is the square root of 81? Well, the square root of 81, well, we all know it's 9. And if I ask you why, you're going to say because. Oh, by the way, if I draw a triangle, a dotted triangle like this with the point down, it means because. So it's my shorthand for because, and that's a recognized mathematical symbol. You may know if the triangle points up, it means therefore. We're not going to use therefore today very much, but we will be using this symbol for the word because quite a bit today. Alright, the square root of 29 is not, the square root of 81 is 9 because 9 is the number we square to get 81. I guess you could call it the reverse or the inverse of the squaring process. Let's try this. The square root of 49. Well, the square root of 49 is, of course, 7. Why? Because 7 is the number we square to get 49. Again, it's like we are working the squaring process in reverse. Usually, if we plug 7 into the x squared machine, we get 49. If we then plug 49 into the square root of x machine, of course, we get 7. So you can see we are working on the inverse operation of the squaring operation. Alright, what's the square root of 1/16? Well, of course, we know it's 1/4. Why? Because when I square 1/4, I get positive 1/16. In other words, 1/4 is the number I square to get 1/16. In general, alright, so we know what square roots are all about. In general, the square root of a is the principal square root, or what we call the positive square root. Well, let me write it this way in book's notation, is the positive number whose square is a. So we are going to agree that square roots are always positive. Okay. All right, and that's again by agreement, by definition. If I ask you to simplify the following expression, what's negative the square root of 225? Now, this negative sign means just that. It means I negate whatever is in front of it. So, well, the square root of 225 is 15, so minus the square root of 225 is, of course, negative 15, just as if there was a factor of negative 1 being multiplied outside of this square root operation. Well, the square root of 100. Well, we know the square root of 100 is 10. Why? Because 10 squared is 100. In other words, 10 is the number I square to get 100. What about the square root of minus 100? Well, you'll have to ask yourself a question here. What number do I square to get negative 100? Negative 100 is inside the root sign here. Well, no matter what I put in there inside that parentheses, if I square it, I will always get a positive number. So there is nothing I can square to get a negative number, as you can easily see. And anytime you're taking the square root of a negative quantity, our book claims that is not a real number. It's an irrational number. Other books have other terminology. Basically, our book says not real, or the phrase not a real number. So the moral of the story here is you can't take the square root of a negative number. Okay? Alright, what about variable expressions? Taking roots of variable type expressions. What do I mean by this? Well, let's see. If I ask you to simplify, for example, the square root of x squared. Let me give you some more room on top here. Right, to try this again. I'll say simplify the square root of x squared. In other words, what quantity, what value, what variable can I square to get x squared? Well, of course, your answer is x, because x squared is x squared, right? We make this agreement, though. Remember, square roots are always positive. And a variable could be negative. You don't see a negative sign in there, but variables can represent negative values. So to be consistent with this agreement that square roots are always positive by definition, we have to put absolute value symbols around that variable. Again, that's if x can be any real number. Our book sometimes gets around this and says if variables, if we previously make the agreement that if variables are positive, represent positive quantities, then I can say the square root of x squared is simply x. So I do not have the possibility then of a square root being a number. And let me make that a little clearer. The square root of x squared is x if x is positive. In other words, if x is greater than 0. Alright, so I'm going to make this assumption for the rest of the day today. If variables represent positive quantities, I'm going to investigate slightly more complicated root expressions and ask us to simplify them. So, for example, simplify the square root of 16x squared. In other words, what quantity can I square to get 16x squared? Well, of course, you're going to answer me 4x, right? The square root of 16 is 4. The square root of x squared is x. And again, it's 4x if we make this assumption that variables from henceforth represent positive quantities. You may notice in some of the homework problems the author does not indicate that all variables must be positive. So you'll see some absolute value symbols coming up in the homework solutions. So be aware of that to make sure you know where those absolute values are coming from in the homework solutions. That's because that condition of x being greater than 0 may or may not exist in the problem statement. Alright, let's try another one here. If I ask you to simplify another radical type expression, the square root of x squared plus 2x plus 1. Alright, no, you can't break up a root sign over a sum or a difference. We'll learn more about that later in section 7.3. But what I can do is recognize this as a square of a binomial. That is going to help us here. X squared plus 2x plus 1, that is the square of x plus 1. If you multiply x plus 1 by itself using the FOIL method, you'll get the trinomial x squared plus 2x plus 1. Remember, you've got an inner and outer product to worry about when you're multiplying x plus 1 by itself. Alright, well, if we convert this original problem into this form where it's the square root of something squared, I'll say, well, it's just x plus 1, right? The square root of something squared is just that something. The square root of x plus 1 squared is x plus 1. Alright, now even if x is positive, I suppose x, well, let's see, if you're adding 1, let's see, if you make that restriction that all variables are positive, we don't really need these absolute value signs, but again, if all variables are positive, we can drop those absolute value symbols, okay? Alright, to some more examples here. Simplify another root expression, the square root of m to the 4th power. Oh, can I slip there? Hang on a minute. The square root of m to the fourth power. Well, what is the square root of m to the fourth power? In other words, what quantity do I square to get m to the fourth power? That quantity is the square root of m to the fourth. Well, of course, m squared is m to the fourth power. Now notice m squared is automatically positive no matter what m is. If I take a negative number and raise it to the second power, I will get a positive quantity. So I don't really need absolute value symbols here. If I ask you to simplify something like this, the square root of 49 r to the 8th power. Well, let's see. Let's stare at this for a little while. There's still a square root. I have to ask myself, what quantity can I square to get 49r to the 8th power? Well, clearly 7 is going to be our coefficient here. 7 squared is 49. Well, I'm going to have a power of r here, and I think you can see that r to the 4th squared is r to the 8th. So I claim the square root of 49r to the 8th is 7 r to the 4th, and again, no absolute value symbols needed. Okay? We've only talked about square roots now. There's other roots. There's higher order roots, which typically are not covered in a first course in algebra, so I want to kind of stretch that idea to include other index roots. I suppose we should talk about what is the structure of a radical expression. If, for example, I'm going to ask you to take the cube root of 27. Well, many of you out there pretty much know what cube roots, fourth roots, fifth roots, etc. are. Some may not. Let me cite this value, kind of tucked in the crease there of the root symbol, is the index of the root. This is what the author would call a radical sign. I would call it a root sign, but either one's fine. And what I would call the stuff inside the root sign, more formally, it's called the radicand. So every root has a root sign, a radicand, and an index. Now, you may say, well, those square roots we talked about didn't include an index. Let me talk about that for a minute. Right? When there is no index specified, we assume an index of 2. So, indeed, square roots are really second roots. All right, so let me write that down. When no index is specified, we make the assumption, and that's by definition, it's a second root, that the index is 2. Right. Let me write that down a little more clearly. If there's no index specified, we assume that the index equals 2. In other words, that you're talking about a square root. Okay, let me get a fresh screen here. Alright, so what about higher order roots or higher index roots? Well, we had the cube root of 27. As you might expect, if you're talking about third roots, well, the third root of 27, it's not the number you square to get 27, it's the number you cube to get 27. I claim the cube root of 27 is 3, and I claim that's because 3 to the third power is 27. Check it out. 3 times 3 times 3 is 27. Right? So if I ask you similarly, what's the cube root of 125? And that 3 should be tucked in the crease there a little more carefully. Right? The cube root of 125, well, the cube root of 125 is 5. And if I ask you why, you're going to say because 5 is the number I cube, not square, but 5 is the number I raised to the third power to get 125. Check it out. 5 times 5 times 5 is indeed 125. If I ask then, well, the third root of 1 1/64th. Well, what's the third root of 1/64th? Well, that, of course, is 1/4. Well, we can hopefully recognize that denominator. 64 is 4 to the third power. 4 times 4 times 4 is 64. Alright, so as an extension of that, I claim the cube root, or the third root, of 1/64th is 1/4, because 1/4 times 1/4 times 1/4 is going to be 1/64. How about variable expressions involving third roots or cube roots? Alright. Minus 27x cubed. What is the third root or cube root of minus 27 over x cubed? Well, I think we can see the cube root of minus 27 is minus 3, and the cube root of x cubed, well, that's just going to be x. I claim it's minus 3x. Hopefully you can see that without too much trouble. And if I ask you why, you're going to tell me because if I raise minus 3x to the third power, I get minus 3x times minus 3x times minus 3x, and indeed that multiplies out to minus 27x cubed. Right? I want to make a note here. Right? If I ask you for the square root of negative 100, you'd give me a response that is not a real number, according to our textbook and according to the custom. But here it's okay to take the cube root of a negative number. Let me write that down. It's okay to have a negative radicand when your index, not only when your index is 3, but when your index is odd. Right? Because I can have an odd string of negative factors resulting in a negative number. Let's go another example like this. Let's try the cube roots. Simplify this following expression. The cube root of minus 2 a cubed b to the 6th power. Alright, I have to ask myself, what quantity do I raise to the third power to get minus 8 a cubed b to the 6th? That quantity is the response to our question. Okay? Well, let's take a look at the number. What number do I cube to get minus 8? In other words, what is the cube root of minus 8? Well, of course, you'll tell me that's minus 2. Note that minus 2 times minus 2 times minus 2 equals negative 8. What's the cube root of a cubed? Well, the cube root of a to the third power is just going to be a. Essentially, the third power and the third root operations undo each other. And similarly, well, let's say, what value do I raise to the third power to get b to the 6th? Well, of course, that's b squared. Right? Check it out. If I put minus 2 ab squared in this parentheses, if I raise that quantity to the third power, I indeed get my radicand, my original radicand. So I claim then the stuff inside the parentheses here is indeed the third root, or the cube root, of minus 8a cubed b to the 6th. Alright, one more I want to do today. This is number 68 on page 655 in your text. And a little nastier expression, but still a third root. Now remember, it's okay to have a negative radicand when your index is odd. If your index is even, no dice, right? So remember that. I want the third root of minus 343 a to the sixth b to the third power. In other words, I have to ask myself, let me illustrate it like this. Right? I want to know what this is. That is my goal, to simplify this expression. So I claim that I need the value or the expression that when I raise it to the third power, I get minus 343 a to the sixth b cubed. Well, I, like probably you, like to kind of break this down into thinking about the numbers first. Let's look at minus 343. What's the cube root of minus 343? Well, I think you'll agree that 7 cubed is 343. 7 times 7 is 49, and 7 times 49 is 343. Alright, so the coefficient is going to turn into a minus 7. The cube root of minus 343 is negative 7. The cube root of a to the sixth is a squared. Why? Because a squared cubed is a to the sixth, and the cube root of b cubed is, of course, b, because b to the third power is b to the third power. So there's my final response for number 68, page 655, right? The cube root of minus 343 a to the sixth b cubed is negative 7 a squared b. Alright, this concludes micro lecture for section 7.1, and that is all for today.